I want to talk about quantum algorithms, mainly algorithms where you can get an exponential speedup compared to the best classical algorithm, and then pretty much we'll narrow it down to algorithms for factoring of integers and for discrete logarithm over some Abelian groups. And I decided I want to have some fun. I'm going to talk a little bit about elliptic curve dlog, which is not usually covered in schools like this, but I'm going to show you some stuff about that. I'm going to show you also about stuff about some stuff about quantum programming. That's an area I'm working currently, and there's a tool called Liquid. Microsoft is developing that, and I'm sure plan to show you some algorithms implemented in Liquid, and some small-scale simulations you can do with that. Obviously, that doesn't scale; it's a classical simulation of a quantum algorithm, but you can do some stuff with that. Feel free to ask me questions during the talk. If it's all way over your head, what I'm going to talk about, this is maybe a nice take-home, what quantum computing is really about. It's really about engineering and computation, so you get cancellations of computational paths. It's something that you never have in a classical machine. You don't have it in a probabilistic machine, where you can have many paths, but it will never cancel each other out. It will only add each other in terms of probabilities. In quantum computing, you can have that some computations cancel each other, and you will never observe these results. If you do it right, if you massage your computation in a certain way, you can do it so that the stuff you're not interested in, you will never observe it, and the stuff you're interested in, you will observe it with some probability. And in a sense, that's what interference of waves is about, right? So it's maybe a take home. We heard already yesterday from Mike Mosca that there are a lot of quantum algorithms, and he showed us some examples, the Deutsch-Josa algorithm and the Simon's algorithm. There are algorithms that are believed to be useful for actual practical problems, and the main focus these days seems to be around simulation of quantum systems. That if you ask people in the community what quantum computers are ultimately going to be useful for, many people say it's for simulation of physical systems. And that's certainly a killer application, so I put it here, and that's the first reason really why people came up with the idea in the first place. But Shor's algorithms, that gave a big boost to the field. It was in the early 90s. He showed that we can actually factor integers that would immediately break RSA. Very quickly afterwards, it was realized that that could also be used to attack elliptic curve signatures, anything that's based on basically computing Abelian groups. These schemes would be broken if a big quantum computer would be around. And what's interesting here is you would get an exponential speed up compared to the best known classical technique. Typically you can't prove anything, like you cannot prove that there's a real separation here with the classical algorithms, because for all we know there could be classical efficient method. Nobody believes that, but there could be. So those exponential speed ups here in that context are always meant to be compared to the best known classical technique. An interesting other algorithm, more recent, was an algorithm to solve systems of linear equations. It's very cool. There's some caveats because you kind of, due to the way you get the information into the system and how you can extract it. But there are some applications for these algorithms as well. I'm not going to talk about the latter one. I'm focusing on the factoring and dlog type algorithms. And towards the end, I want to talk about something called hidden subgroup problem, which tries to generalize these ideas to other groups. All right, we heard already a bit about gates. I just want to recap a little bit and establish some notation. So there's this graphical calculus for quantum algorithms, which is extremely useful because it's very concise. It allows you to specify algorithms basically as diagrams, kind of like classical circuits. And what you have here, for instance, can I go on this thing? Great. What you have here is a gate. That's the Hadamard gate you saw in Mike Mosca's talk. It's a 2x2 matrix. It's unitary. You can see it as a Fourier transform for the elementary Abelian 2 group. Each line corresponds to a qubit. Okay? And if there's a line like this one, where you don't do anything on it, then mathematically that really means that the identity is happening on that line. And if it's not connected to the other line, it's a tensor product between the two operators. So that's implied by the notation. So you have on the left hand, you have always the graphical calculus. On the right hand, you have a corresponding unitary matrix that's underlying that operation. Sometimes it's helpful to think about the unitary, sometimes it's more helpful to think about the circuits. Sometimes they get other structures that you might want to think about that represent the circuits that might be easier to work with. But it's kind of, the trick is to know at what level you want to work at. Sometimes better to work at higher level, sometimes better to work at a lower level. This circuit here is just a swap between two qubits. Mathematically, that is this matrix, it's a permutation matrix. And down here we have an operation U that's applied if and only if this bit up here, let's call that B. Okay. There's a bit B, which can be 0 or 1, or it can be a superposition of 0 and 1. And this operation U is applied if and only if this bit B is equal to 1. If it's 0, then you do the identity. So that means basically in that branch where B is 0, you do the identity. And in the other branch where B is 1, you apply U. Right? And those are the coefficients. So those are very useful to build up bigger unitaries. We have these control operations. Okay, so here for more examples, we've seen yesterday the Hadamard transform. You can write down the unitary matrix like this. You can also write down the so-called Bra-Cat calculus, very popular in physics. Okay, so it's just vectors really. These are vectors and these are covectors, so linear forms. And what's nice about that calculus is if you have a covector and a vector, you get a scalar. And if you do it the other way around, you get a rank 1 projector. And we've seen some of that in Renata's talk this morning also, using these kind of operators. So you have different ways again to represent the same operator. H2 is the 2x2 Fourier transform. You can write down that matrix. You can write it down in this form. You could write it down in a graphical form. If you tensor this H2 n times, you arrive at this operator. You can write it very concisely. It's just saying instead of going xy over a bunch of bits, you go over bit vectors. Okay, so f2 to the n is just the bit vectors of x n, ranging over all bit vectors for x, ranging over all bit vectors for y, and you get a matrix that has only plus minus 1 entries. Turns out to be a unitary matrix, and it's again a very useful transform in quantum computing. It's a Fourier transform for the elementary Abelian 2 group. Okay, any questions so far? That's probably pretty basic. Let me talk about how to build up large-scale operations. That's called the universality theorem. I will give you two flavors of that. One is the exact universality. So if you have a continuous set of rotations available, you can actually, in theory, implement any unitary. But that's not a really realistic scenario. It's more realistic to assume you have a discrete set of operations. Then the question is, how well can you approximate using that set? So I will give you just a flavor or a hint how these two scenarios play out. So in the gates, typically you have something like this, like local gates, where you just operate on one subsystem of the quantum computer. You apply an operation. And then what it will do on the Hilbert space is you get a big block diagonal matrix, all right? So by just affecting a tiny piece of the quantum computer, think physically, maybe you shine a laser or you apply a magnetic field or something like that, but you're just part of the system. You affect an exponentially big operator on an exponentially big space. It will act non-trivially, and it will only cost you the cost for that one operator U. Very different from classical, say, HPC, like high performance computing, where people would be happy to have an operator like that too, because it's kind of very local. It would be even cache local if it were like this. But you would have to pay the price that you have to do each of these blocks classically. Right? Quantumly, we only have to do one block of U, and it will be automatically affecting all these other little blocks in the memory. Okay? So that maybe gives you a glimpse why quantum computing is so powerful. Just doing a tiny operation affects the entire Hilbert space. So here's another operation. That's the so-called controlled knot that we saw yesterday. It's a permutation. It acts on 2 qubits, and it has that matrix here. It cannot be written as a tensor product of local operators. And it turns out that if you throw these two ingredients, 1 and 2 together, you can, in principle at least, get any operator on n qubits. Okay, as a sequence of either C naughts or these local operations. That's the content of that famous theorem by Barenko et al. They show that if you have local operators, if you have C naughts then you can express any unitary as a word of finite length in either local or C0. Okay? Of course, the length of these words, they grow dramatically. It's no wonder, because our operators also have sizes that are exponential, but at least we can express them in terms of these operators. All right? Does it make sense? Of course, usually we're not interested in implementing operations that have an exponential cost on a quantum computer. We're looking for operators that have very concise circuits, okay, that we can express using a short word, and they still have a meaning for an algorithm. Okay? So that's much more useful. And the prime example for that would be the Fourier transform, which we will show to you in a minute. Okay, so that's kind of an example where you can express it using local operations and C0s, but the word length to express it will be polynomial in this parameter little n, as opposed to being exponential in this little n. Right? But at least it's very nice to know that we could in principle implement any operator in qubits once we have these guys and once we have these guys. Okay? And like, just to give you a hint how that's proven that you can express it, it goes through these so-called Givens rotations. Those are operators that act on just a two-dimensional subspace, and it's well known that you can factor any unitary as a product of Givens rotations. Okay, and just jump here ahead. So now what you can do is you can arrange these Givens rotations in a very specific way. Then you act on these two-dimensional subspaces in a way that when you pick the next one, you do it in a way that they differ only in one bit position, these two subspaces. So the next one will only differ in one bit position. And so you line them up in a very specific way called gray code. If you go through the gray code, then it can be shown that you will need precisely 4 to the n gates. And that's kind of tight because there are also 4 to the n real parameters in a general unitary of size 2 to the n by 2 to the n. And so it's tight. So generically you cannot hope to get anything better, but also one can do it with 4 to the n operations generically. Right? That doesn't mean like for a specific operation you can of course do better, but if you don't assume anything about the operation, 4 to the n would be it. There's a bunch of papers here, and I also compiled a list of further reading at the end of the slide deck, so you can have a look at that too. Most of the papers are on the archive, as Anne mentioned yesterday, so that's a really good thing in our community. People usually put their papers on the archive. Okay, yeah. It's not realistic really to assume that you have arbitrary rotations, because then you would have angles that are given by any real number essentially. So in practice you'll have to work with a discrete set of gates, and that set of gates will generate a subgroup of the entire unitary group, and hopefully it will be such that it's dense. So that means that for any given unitary you will always find an element in that discrete group that's arbitrarily close. Right? For any given unitary and any given epsilon you find some element of the discrete group that's epsilon close. And there are several very popular gate sets. The verdict which one is the best for quantum computing is still out, and it depends a lot on the architecture and on the particular fault tolerance strategy that you use. But a nice one is called Hadamard and Toffoli. That's known to be universal. Another is the so-called Clifford and T gate set. I'm not going to define really what the Clifford group is, but like just to give you an idea, it's the C0 together with a gate that looks like this. It has phases 1i, and you take the Hadamard, the C0, and then you get this guy, this T gate, which is 1 and a primitive 8th root of unity. Okay, so you throw them together, you allow them to be applied to any qubit or any pairs of qubits. You get a discrete group, and that group is known to be dense in the set of all groups. A set of all unitaries. Why are these interesting? Well, you can apply them in a fault-tolerant fashion, these gates, for many codes. For instance, the Steen code is surface code. They are popular choices for fault-tolerant implementation of quantum computing. I'm not going to go into that, but it's very useful to keep in mind that that's where actually the cost will come from. If you want to implement a quantum algorithm on an actual computer, most of the cost will sit in these operations, and in particular it will sit in the single qubit rotations, not in the controlled knots. That's kind of funny because you might think the control knots are the harder ones. That's true if you work at the physical level. Definitely, it's true to interact two particles. Doing it with like an entangling gate between two particles is difficult. But if you're at the logical level, at the fault tolerance level, for many of these codes, it turns out that the C knot is relatively easy to do, but a T gate is very difficult to do in a fault tolerant fashion. So many times when people look at the complexity of a quantum algorithm, they count the number of T gates that you would need to implement the algorithm. That's kind of an underlying complexity cost measure. And yeah, as I said, single qubit rotations are really expensive. So it's always good to try to minimize them in your algorithm. Okay, cool. I'm going to skip this slide. This is just about the Toffoli gate that Mike mentioned yesterday. It's a good constituent. You can build many reversible operations from it. And here you have this T gate as a basic building block. And you can see that you need 7 of them to build a single Toffoli gate. You need 7 of these T gates, and each T gate is incredibly expensive. Think of your computer having some areas whose only task is to prepare T gates, and it would be like a factory churning out T gates. Like the majority of the area of the chip will probably be dedicated to just make T's. And then once you have enough of them, you can do stuff like this Toffoli gate. But even to do just a single Toffoli gate, if you do it this way, you need 7. If you can find a good code which has a built-in Toffoli, maybe you could do it with less, but there's no good way, at least not that I know of, to do it. So presumably you would have to do it this way with the T gates. But this slide just to give you an idea that even doing one Toffoli gate is expensive. Okay, so how does approximate universality work? There's a beautiful theorem due to Bob Solovey and Alexei Kitaev. They showed that if you have a discrete gate set and you got a fixed dimension, take a unitary in that fixed dimension. SU means that the determinant is 1. That's just a technical thing, really. You might as well think of UN here. You have a full unitary group. Then you can always find approximating sequences that are short, meaning that for your given epsilon, you find a sequence of length, a polynomial and the logarithm of 1 over epsilon, that epsilon approximates it. And that C is roughly 4. It's the best, for a long time people thought the best choice of C would be 3.97, and people thought maybe you can bring it down to 3 plus delta. But this is a sort of like a method that's completely oblivious to the gate set, and it will work for any gate set. As long as you know it's dense, you can always efficiently approximate. Very nice in theory, but in practice you want to have something shorter because a quartic polynomial is terrible to work with. If you want to have an epsilon of maybe 10 to the minus 20 or so, which is not unrealistic for some algorithms, we're going to have to go that far down. And if you then scale with epsilon. If you then scale with log 1 over epsilon to the power 4, right, that's terrible because you get like 20 to the 4. For just one operation, you need that many elementary gates. Okay, and not even mentioning if you have to go further down here, I don't know, minus 50, and you're looking at a huge cost for implementing these operations. So that's why the Solovey-Kitaev theorem is very nice in theory, but in practice, if you know more about your gate set, there are better choices. I'm going to skip this. This is about the idea how the Solovey-Kitaev theorem really works. Starting basically from an initial set of gates, and then you refine that set of gates you approximate. I'm going to skip that. If you know something about your gate set, there are better procedures. In particular for Clifford and T, you can do it in kind of a two-step, 1-2 punch procedure. First, you round off your unitary into a domain where you have a symbolic representation of the matrix. Okay, initially you have maybe a numerical representation of the elements, then you represent them here, right? And that's symbolic because you only have the complex fourth rule of unity and 1 over an algebraic number. So all the entries are now over that domain. And then from there is an exact synthesis algorithm that takes any operator like this and finds a factorization. It's not unlike Euclidean algorithm, it's not quite your Euclidean algorithm. Well, to tell you the truth, it is the Euclidean algorithm, but you have to go to a different domain. It's no longer unitary, so you have to work with quaternions, and then you can interpret that again as sort of a Euclidean algorithm. But the bottom line is that you can improve the complexity a lot. You can do, you can find approximating sequences that only scale with log 1 over epsilon instead of that polynomial, if you do it that way. And shown on the right here is just if you look at the elements of that discrete group, how they scatter along the set of all unitaries. I'm plotting only the upper. This is a 2 by 2 matrix, and I'm showing only the upper left entry. Right? That's going to be a complex number of absolute value less or equal to 1. I'm kind of going to show only that quadrant, right, in the complex plane. And the blue spots are the things you can actually get by an element from that discrete group. And you see it very uniformly fills that up. It's hard to prove anything rigorously about how quickly it fills up and showing that you can look up the elements, but it just turns out that it works beautifully in practice. If you make some assumptions about that, the distribution, how many elements you find within a small radius, and they seem very reasonable. They just rely on some distribution of primes. Then you get a scaling of log 1 over epsilon. I can tell you more about that. It will take us maybe a little bit from the topic of this lecture, but there's a lot of work, mainly from Vadim, and there are other groups who do work along these lines too. There's a big industry around these factorizations these days. Okay, let's switch gears. We'll talk about the Fourier transform. So maybe briefly, the compiling problem is you want to take a high-level algorithm, compile it down to a gate sequence. And how do you do it? Well, you first go through like a representation where you have C-naughts and local gates, and then you represent each local gate by a discrete approximation. And then you implement those in turn fault tolerantly on an error correcting code. That gives you a whole another layer, because that, like each T-gate, for instance, will have to be distilled by a factory. So there's a multi-step process to implement anything on a quantum computer. Okay, so let me talk about Fourier transform. We'll see in a moment why it's very useful, but let me just as a warm-up show you why it's so useful. Even classically, of course, everybody knows Fourier transforms are incredibly useful in compression, for instance. And Fourier transforms are nice because there's a fast algorithm. So if your signal has length m, then you can compute from time domain, you can go to frequency domain in essentially n log n operations, say counting arithmetic operations that you do on the data. So if you have, say, gigabyte of data, which of course nobody does, nobody computes a Fourier transform of a gigabyte of data, but if you were to do it, you would maybe need like a billion floating point operations, something like that. But on a quantum computer, things are much, much better in that respect. So it basically scales linear. Well, if you're very careful, you start out with a quadratic cost here, but it turns out then that you can shave that even down. So let me put linear here. It's more like log n, log n, but just for the sake of the argument, if you were to do a Fourier transform on a gigabyte of data quantumly, you would only need a very small number of operations. Basically nothing. Think of a Fourier transform of a signal of length n. Basically it's free. All right? It's just a very small number of operations you need to do. Almost like in an optical computer where we have a light wave. And if you want to Fourier transform it, you can put a lens and it will just do that by propagation of light. And a quantum computer does a similar thing. So if you apply this very short sequence that I will show you in a moment, that very short sequence will turn the signal into a frequency representation. And you can go back by just doing essentially the same operation. You come back to time. Any questions about that? That's really at the core of Shor's algorithm, that this is so fast that you can go from time to frequency so fast. And that's a unitary operator. That's really at the heart of Shor's algorithm. Okay, and what you see down there is that you can kind of sometimes extract some peaks from a signal. So if your function is periodic and you Fourier transform it, you will see usually some peaks to tell you something about the period. Okay, and that's kind of why we want to use the Fourier transform. I'll show that to you in a moment. First of all, what is the Fourier transform? Well, mathematically it's very simple. You just need a primitive nth root of unity. Then you can write down this matrix. And it's very simple to check that this is indeed a unitary matrix for any choice of n, actually. And then if you have a signal, say this could be an image, so you got a two-dimensional signal. You could Fourier transform the rows and the columns of this image, then you get something that looks like this. This is just a power spectrum. Of course, I cannot really visualize the complex numbers here in a nice way. So what's done here is that I did the absolute value squares of the Fourier coefficients. And then typically what you see is that if it's a real-world image, then that will be concentrated somewhere in the low frequencies. It's very kind of very untypical that you would get a lot of high-frequency components in the Fourier transform, right? Whereas if you take a random function, of course, you take a Fourier transform, it will be all over the place. But if the function is kind of smooth and slow varying, then it would be typically concentrated in the low frequencies. Okay, cool. So how do you compute the Fourier transform classically? Well, there is the Cooley Tukey Fourier transform, which factors that matrix, the Fourier matrix, into a sequence of matrices, all of which are sparse. Sparse in the classical sense, right? Classically, people care about having something like a permutation matrix, which is just extremely sparse, right? It's just reordering in memory. Or this operator, which is block diagonal, it's nice. This is just another very sparse operator, and here you got another sparse operator. So classically, that's extremely useful because now you can recurse, and you get an n log n algorithm that way. Quantumly, it's even better, and to understand that, it makes sense to look at the matrix and what happens when you generate this. Okay, so this is what it plays out to. If you take the Fourier transform of length 2 to the n, and you reorder the rows in a very special way, that reordering of rows is essentially a coset decomposition of the cyclic group of order 2 to the n by the subgroup of order 2 to the n minus 1. Right? This is a subgroup. And now you order the cosets in a particular way, so basically even odd, even odd, even odd. So that permutation then reorders it in that form, and now you see this essentially there's only DFTs of one number smaller, right? The DFT 2 to the n gets reduced to 4 runs of the Fourier transform of one length shorter, but it needs to be decorated by something. So here there's a certain matrix, and that matrix is so-called twiddle matrix. Actually, this is the Pruning matrix. It's like the consecutive powers of omega to the n. Right? You go in linear order. You have exponent 0 here, 1, 2, and so on. And then you take also the direct sum with the identity matrix. If you do that, then this guy here will pick up these two W blocks, and overall you get that beautiful recursion. So that allows you to implement a DFT of length 2 to the n by first doing the inverse of that pi. Then you do a smaller DFT, and of course there you just recurse. Then you do the Tn, and then you do just a 2 by 2 Fourier transform. Right? And the 2 by 2 is just a Hadamard, that's easy. Here you will just recurse, so eventually you will arrive at Hadamards as well. And the only difficult part really is these Tn's. Right? But the Tn's again are nice because they're just an identity, and then this W matrix. And it turns out that the W itself is a tensor product, so it's very cheap for a quantum computer. And having a tensor product with an identity here, it just can be done with controls. Right? You just need a little bit of control operations. I'm skipping details, but you can find that in the literature. I'm citing at the end of the talk. This is the circuit you arrive at the end. As you can see, there's only Hadamards. Okay, you get exactly n Hadamards, and you get these controlled rotations. And each controlled rotation will just perform a tiny rotation by some angles. So they all look like this, basically. 2 to the n to some pi. That's what these guys here, these Tn's, what they look like. Right? And you do need to do it in a controlled fashion. That's because you want to do the identity on one block and this tensor product on the other. If you study the recursion, it turns out classically you reduce a Fourier transform of length n to 2 runs of Fourier transform of length n over 2. If you solve the recursion, you get n log n. Quantumly, you get 1 run of length n. It's just the cost of n over 2 plus something of cost log 1 over x, log n, sorry. And you see that from here, the cost for one run of length to the n is one run of length to the n minus 1 plus something that's of cost log n. Okay, so that's a very nice recursion because now you just pick up a quadratic cost overall. And it gets even better than that, one can even shave down the cost by pruning these rotations. So because some of these would be very, very small, so you don't even feel them. They're very tiny angles, they don't matter much for the overall algorithm. And so if you just do some thresholding where you say, I'm going to crop these, once kind of that distance here between the I and the j label tells me how small that omega has got to be. Right? And if that gets too small, if I then just ignore that gate and replace it by an identity gate, you arrive at something we could call QFT NK. So K now controls how much we approximate, right? If we make K very big, we just get QFT N. But if you make K very small and the limit K equals 0 gives us something like the Hadamard transform. But we can interpolate nicely in between. And it turns out, and Don Coppersmith had a paper very early on, saying that like if you essentially choose only log n of these, right? Keep only log n of these controlled rotations, you get an epsilon approximation of your QFT. So in practice, you never want to do all the rotations. It's enough to do only log n of them, and you get a very good approximation to the operator. How am I doing in time? All right, I need to speed up. All right, so factoring. Integer factorization, I think a lot of people from crypto are here. I'm preaching to the choir. I think if I tell you that the best known algorithm is something sub-exponential, it's the number field sieve. Here's the runtime. That's, as far as I know, still the best algorithm to tackle factoring generically. And quantumly, the idea to factor is very, very different from the number field sieve or quadratic sieve. All these approaches very different. It uses a kind of very simple idea, namely the reduction from factoring to period finding, which is well known. People knew that since the 70s, probably earlier. That if you could find out a period of a map like this, right, take a fixed element, say A, mod n, and if you were magically able to get the period of that number, of that element, mod n, if you could infer that, then you could factor it. And it's very simple. If you knew that the period r, say if it were even, then all you need to do is take a to the r minus 1 and compute the GCD of that with the number n. And that will, with very high probability, give you a non-trivial factor between of this number n. It specifically works really well if you have an RSA number, right? Only 2 big primes. And if you have an element A mod n, and if you magically were able to get the order, with very high probability it would be even. And then you would just take this and compute a GCD would give you one of the 2 prime factors with very high probability. Okay, but classically it's not really useful because you cannot compute the order classically, right? It's an exponential order. You would just keep exponentiating forever and then until you finally get back to 1. But quantumly, it turns out, a quantum computer can perform this exponentiation for an insane range of inputs. So essentially, think of all the values of x ranging from 0 to n minus 1. And even more, actually, in Shor's algorithm, you don't do it till n, you do it like till n squared, roughly. You get all these inputs, and you evaluate the exponentiation map for all of these inputs with only one operation. Okay, and the quantum computer can do that because of the principle of superposition. Quantum computer can do it. And then you get a state which is supported on all inputs and all outputs, okay? And it has a certain periodic property. So you can visualize it maybe like this. So here are all the inputs to the exponentiation map. Here are all the outputs, and you compute the map that takes x goes to 2 to the x. Say in that case, 2 would be a primitive root. In general, we would pick a random element mod p, and with high probability would be good because we would have full period. And as you can see, the state is periodic, right? You can get maybe a sense that, all right, this is roughly the period here. Right? And the question is, of course, how do we extract it from this representation of the state? How do we get it out in our classical domain? It turns out you cannot just measure the state. It will not reveal any information at all about the period. If you were just to create that state and measure it, one can prove there's no information. And the issue is that you don't know really the offset. If you measure, you will collapse it. It will look periodic, but it will have an offset that is annoying. And mathematically, what happens is this. So you would kind of start with the X register and the Y register in a fixed state. Then you create all the inputs to the exponentiation map. Then you compute the exponentiation map for all the inputs. That's the map F here. That's exponentiation. And then you would observe this second register. Okay? That's actually something you only have to do for the sake of the argument. In practice, you don't even have to observe it. It will equally work if you just ignore it from that on. Then, as you heard from Renata's talk, if you ignore part of the system, mathematically you trace over that part. And one can show that the algorithm works equally well if you just trace over that register and ignore it from then on. You can still learn the period that way. What happens though if you were to measure it, and it's easier to think about in that case, at least I find it easier, then your state will look like this. It will be periodic. The period R will be the spacing between these peaks. And but unfortunately you will have some offset here that you cannot control. If you do it again, you set up a state and you measure the second register, you very high probability you get a different offset. So that doesn't really look very useful. But it was Shor's really nice idea that you can get rid of this offset by taking a Fourier transform, right? Because what happens then is, then that offset will just go into a complex phase. If you shift the signal and time domain, and you go to frequency domain, right? You Fourier transform the function. What happens is you pick up a complex phase that depends on how far you shift it. But if you then just measure in the frequency domain, you will not feel that complex phase because measurement is kind of ignorant of a complex phase, you get the same result. And so the only twist is when you do that, then your period R will turn into the inverse period, 1 over R. Okay? And so kind of the twist in Shor's algorithm is that you can still extract R from 1 over R, even if you work with like finite precision, if you work with Fourier transforms of length 2 to the n and so on. That's really the technical meat of Shor's paper, is to show that it's possible, if you do these steps, if you create the initial state, create that superposition, evaluate the function, measure to set up that periodic state, and then Fourier transform it, and then measure, you pick up a number. So the meat of his paper is that you then can infer the inverse period, which is always like a number like this, from from the number of this form. Okay, and the number of this form will typically have q of a form 2 to the n in the denominator, and p is some number, and you try to find the number that's closest to that number that has this form, 1 over r, which is the r we're looking for, and as L0 is some integer. And for that he uses continuous fraction expansion that gives you kind of the best approximation to the number you have measured. And it turns out that the denominator must be r, and you reconstructed this R. Right? So that's in a nutshell how the algorithm works. Yeah, it's kind of using the fact that you can follow two paths and do something really impossible classically. Only Chuck Norris could do it, maybe. I don't know, do you guys find Chuck Norris jokes funny? Is that popular joke? And you can bring together these paths also, right? You can make them cancel again and follow two paths that you could not follow classically. Right, I'm gonna skip this. How much more time do I have? 5 minutes? Okay, I'm gonna skip this part. This is like, you can analyze the resources, and people have done many back of the envelope calculations, how many gates you actually need for Shor's algorithm. Some of these arguments are not really useful because they ignore the underlying topology of your computer, right? What gates you actually have available. But if you want to do some really rough estimates, if you want to do Shor's algorithm for an n-bit number, and you push everything to the limit, you can do it in principle in 2n qubits, which is pretty good. The number of operations, like a safe bet is to say you need a cubic number. People even investigated methods for fast integer multiplication. You could bring it using Schönhagen-Strasse, you can bring it down to n square, log n, log n, stuff like that. But it's not really realistic, I think, because the number n would have to be very big for that. So I think it's safer to assume something like a cubic cost here. So then you get something like this. So factor a 1,000-bit number. You only need a few thousand logical qubits. The number of operations is kind of high. It will be probably in the like hundreds of millions or so. And Mike Mosca mentioned something very similar yesterday. It's possible to do a much more refined analysis of this, but I'm not going to get here into that detail. And so this is actually something I'm quite passionate about. So the question is, what makes Shor's algorithm really work? What's underlying it? I mean, we can go through the steps and convince ourselves that each step works, but what's really going on here? People thought quite a bit about that. There's no ultimate answer as far as I know, but people try to abstract from the case of a cyclic group to other domains. So here's a definition of a problem that you can do whenever you have a finite group, whenever you have a map which has sort of a period. A period just means that there is a subgroup of the group for which the function is constant, right? So you can say the function is periodic, and you also want to have that the function has exactly that period. So you want that the function is constant on cosets, right? That means kind of you get peaks where it's constant, and if you're in a different coset, you want to have a different value. Maybe let me denote it like this. So if you're in a coset, get a different function value. If you're yet in a different coset, you get yet another value, right? It's always shifted, so it's always a coset. So if you collapse the state, you will always get a superposition of a coset. That's exactly what happens in Shor's algorithm, but you can generalize it immediately that way, so that when you would measure a function value, you would collapse the state to a coset. It's a very powerful framework. Unfortunately, we don't know many groups for which this really plays out. And in particular, as far as I know, nobody really knows what to do with these function values other than ignoring them. Nobody has any reasonable sense of doing anything else as far as I know. But it would be really cool if we were able to do any hidden subgroup problem. We would be able to do some lattice problems. And we would even be able to do graph isomorphism. In part 2 of the lecture, I will give you a hint how these reductions work. And the dihedral group in particular, it's such a simple, sorry for the pun, but it's such a conceptually simple group that it's really surprising that we can't do we cannot do the hidden subgroup problem for that. The issue kind of is that you have very many reflections, and if the hidden subgroup is one of these reflections, it's hard to extract the information about the reflection. Regev showed that if you have an instance of a unique SVP problem, it needs to have a gap of a certain polynomial here, which I think is n to the 1.5, but I have to look it up. This problem can be reduced to an instance of a dihedral hidden subgroup problem. So if we had an efficient quantum algorithm, we could solve these instances of SVP efficiently. He also showed that if you were able to solve certain subsets of some problems, and you don't have to solve it in the worst case, average would be enough, you could actually solve the dihedral hidden coset problem. Okay, I think I'm gonna, let me mention this part, and in part 2 maybe talk a little bit about implementations. So, the underlying group, if the underlying group is abelian, like in the cyclic case, then it's easy. More generally, if the group is abelian, it can always be, you can always solve the hidden subgroup problem efficiently. In particular, if the group is the group of points on an elliptic curve, which is an abelian group, then you can always solve the hidden subgroup problem. And think of the instance of being like you fix a point, you look at the multiples of the point, that's a cyclic group, and now you solve the dlog problem in that group, right? So you pick a curve, say in Weierstrass form, pick a fixed point, that's your base point, get another point you want to compute a dlog. That problem can be completely implemented, it's completely solved on a quantum computer at the high level. We know that it can be done. One of the questions is sort of how do you actually implement it as a circuit? And then we get into the nitty-gritties. We would have to look into the formula, how to implement the group law for that elliptic curve. I think it's very interesting, the databases that have formulas. And we can look at the formula and try to implement the formula using a quantum computer, the arithmetic. But then conceptually, the algorithm looks very much like the factoring algorithm. You start with 2 registers, right, and create all the inputs. Then you evaluate all the multiples of the point, the generator that you're given, and the point that you want to compute the dlog of. Right? So we have our generator P with our point that's in the span of P. And we know these points are completely known classically. So we can certainly come up with a map that takes an integer k and does just scalar multiplication k times p. And likewise for q, we can do scalar multiplication with q. We can come up with a circuit that creates the state, no problem. If we now measure the second register, or in that case it's a third register, right? What will happen is that superposition will collapse only to those pairs KL for which you obtain that very specific value that you measured. And that's going to be again in the group. It's going to be some group element. You cannot really control which one it is. It will be some beta times t. Okay, and then like what will happen is that only those pairs KL will show up such that k plus alpha L, where alpha was that, right, so Q is alpha P, will be equal to beta. And that's kind of a line in a 2-dimensional space, right? It's a line with a slope of minus alpha. So Shor figured out that if you now take a Fourier transform, right, what happened to that line? What happens to that line is it's a line with slope minus alpha, but it's also shifted off by beta, right? And beta again we cannot control. But if you Fourier transform, you get a line with slope alpha, there will be no offset, and if you sample from that line, you just get the slope. And you actually sample from the line, you get a pair of points x and alpha x. You get that, you have the classical information about that. And so now the only issue that could happen at that point is that x is maybe not a unit. Right? If x is not a unit, modulo whatever domain you work in the first register, if it's not a unit, then you cannot just divide it off. Right? If it is a unit, then you can just take the second value, ax, and divide it by x, and you get your, alpha x, and you get alpha. Right? But it turns out, if you analyze it carefully, it's very likely you get a unit, and then you get the slope out of that method. So pictorially, what happens is you get the shifted line with some slope you'd like to learn, but there's some annoying offset here that you'd like to get rid of. By using the Fourier transform, you get a perpendicular line, and the amplitude will be perfectly, it will just be perfectly going through the origin at a certain slope alpha, right? This has slope minus alpha. But the information about that offset goes into the phase. And you don't care about the phase because you will measure it in any case. Okay, and if you lay out the operations of the algorithm, it looks roughly like this. So this piece here is just to create the initial superposition of all inputs. This piece here is just to implement k times p plus l times q. So kl goes to k times p plus l times q, where p is a point on the curve and q is a point on the curve. Right? And you know what they are, so you can actually figure out what these boxes are. And then at the end you Fourier transform. And you can even improve that circuit, because typically what will happen is you do that and you measure at the end. There's a very nice paper, I think it was originally by Griffith and et al. They realized then you collapse all these gates in here, and at the end you really just need kind of that register down here plus one extra qubit. That's enough to run this entire circuit. And you don't even need these qubits up there. Only one is enough if you're able to adapt the phases in a certain way. Okay, I think that's it for part one. As I said, there's a bunch of books and papers that I recommend. There are, of course, tons of papers on this, but they are maybe good starting points. And in part two, I'm going to talk about a little bit about how to implement the dlog in liquid, so you can simulate a small-scale example. And I'm going to talk about the hidden subgroup problem, and there's something called the hidden shift problem, which is related to the hidden subgroup problem. But it's an attempt to use a quantum computer to extract convolutions, to perform convolutions and to extract periods in a different way. All right, thanks a lot.